The star is a hard white coin in a sea of black. And close to it, closer than feels safe, there's a world that should not be there. WASP-121b, an exoplanet so near its sun that night and day feel like the wrong words. What matters is this: it radiates, it glows, but the glow didn't behave. The curve we drew from the data light sorted by wavelength, a kind of thermal fingerprint, refused to fit the simple story we expected to tell. Not clean, not obedient. A jagged line that wouldn't sit down on top of our best model line. And in that refusal is the episode's promise: MIRI emission versus calibration drift. What we know, this is the cosmic checkpoint. Before we chase meaning, we pause at the edge of certainty, because in exoplanet science, the first question is never what does it mean. It's what exactly did we measure? Here's the grounded truth. A hot exoplanet emits infrared light heat shining into space. When we do spectroscopy, we aren't seeing molecules directly. We're measuring brightness in thin slices of wavelength, looking for patterns that suggest an atmosphere is absorbing or emitting more strongly in certain bands. That's the promise a spectrum can carry information about temperature and composition. And WASP-121b is a tempting case. It's an ultra-hot world where thermal emission can be strong enough to measure detailed spectral shapes. If you want to test how far our methods go, how much an atmosphere can be read from faint light, this is a place to push. It's not the habitable zone. It's not a candidate for signs of life. It's a proving ground, a loud signal with quiet traps. The key question at this checkpoint is simple, and it's the hinge of everything that follows. What does glow from an exoplanet atmosphere actually mean? And why would a spectrum refuse to fit? The first part, what glow means, is straightforward. The glow is the planet's own heat. It's energy the planet is shedding after being blasted by its star. In the language of retrieval, our attempt to infer the atmosphere from the spectrum, that heat is the starting constraint. If the planet is brighter at one infrared wavelength than another, something about the atmosphere's temperature structure and opacity is shaping the escape of radiation. A mismatch between the measured emission spectrum and a simple model can point towards something complex in the atmosphere. Unusual temperature gradients, unexpected energy transport chemistry that isn't behaving like a tidy equilibrium. But now the second part, the refusal. In exoplanet work, a spectrum that won't fit is not automatically a discovery. It's a warning light, because the same shapes we interpret as atmosphere can be created by things that aren't the planet at all. So we name the tension plainly signal versus artifact, planet atmosphere versus instrument systematics. Imagine a line on the screen. One line is what a physically plausible atmosphere would produce given certain assumptions. The other line is what the telescope delivered. And between them is a gap that won't close. That gap is where excitement lives and where self-deception breeds. Here is the honest fork in the road as the title frames it. One possibility is that WASP-121b's day side is telling us something real and strange, something our current atmospheric picture doesn't capture. Perhaps the temperature profile is sharper than expected. Perhaps the radiating layers sit at different pressures than our simplified models assume. Perhaps the atmosphere isn't a uniform blanket, but a three-dimensional moving structure, hot wind steep gradients compressed into a one-dimensional spectrum. And then there's the other possibility, equally powerful, calibration drift. In infrared spectroscopy, small time-dependent changes in detector response or thermal stability can tilt a spectrum, stretch its slope, or carve out false bumps where a molecular feature would normally be. That's not philosophical uncertainty. That's a concrete confounder instrument systematics that can mimic exactly the thing we're trying to infer. This is why the words refuse to fit matter. It's not just drama. It's the moment exoplanet science becomes a discipline rather than a wish. We don't get to decide what the planet is until we decide what the instrument might be doing. An Earth analogy helps, but only briefly. If a bathroom scale slowly misreads, your body doesn't change, but your story does. 2 steps on the same scale, 2 different numbers, and you start inventing causes. That's how false positives are born. Then we return to the exoplanet with spectroscopy. The number is the calibrated brightness at each wavelength. If calibration drifts, the curve changes, and retrieval can confidently explain the wrong curve. So the evidence moment here is not a number, not a trophy. It's the mismatch itself. A measured emission spectrum that refuses to fit comfortably into the first simplest model we would like to use. That mismatch is the narrative engine and also the test. What do we do at a cosmic checkpoint? We slow down. We ask which parts of the glow are robust and which are fragile, which features persist no matter how we handle the data, and which can be nudged into existence by detector behavior. That is the real beginning of what we know, and we keep our honesty tags close. We can measure a spectral shape. We can translate that shape into constraints on temperature, structure, and opacity if the calibration holds. If the mismatch is real, it could point to atmospheric complexity or variability that we can only glimpse in this data mode. But tonight we don't resolve it. We name it. Because every claim we might someday make about signs of life, or even technosignature hints, in an exoplanet atmosphere will have to survive this same tension detection versus interpretation, meaning versus measurement signal, versus the ways instruments can lie without intending to. The curve is still on the screen, a jagged confession that won't align. WASP-121b glows and the glow refused to fit, and until we know whether that refusal belongs to the planet or to calibration drift, we have no right to a headline, only to the method. So we turn calmly toward the machinery of knowing. If the message is real, we have to learn the language it came in, how a MIRI emission becomes a spectrum we can trust, and where that trust can break. A stream of photons arrives like dust you can't see until it hits glass. The detector doesn't know it's looking at an exoplanet. It only knows it's being asked again and again to count faint infrared light and stay honest while it does. On the screen before the science feels like science, there are raw frames, uneven, speckled alive with instrument behavior. Then a second image, cleaned, corrected, aligned. It looks calmer, more believable. And that calmness is exactly why we have to be careful. This is the one place in the episode where we're allowed to open the hood. How we know. MIRI emission spectroscopy from photons to atmosphere. The key question is not poetic. It's procedural. How does JWST/MIRI emission become a claim about WASP-121b's atmosphere? And where can the chain bend? Start with the simplest fact. We do not see an atmosphere. We measure light, then use spectroscopy to turn that light into a spectrum brightness as a function of wavelength. For a hot exoplanet like WASP-121b, the light we care about is its own thermal emission heat, radiating away. The crucial trick is separation. The star is a floodlight. The planet is a coal ember. To isolate the ember, we need a moment when it's hidden. In emission work, that moment is the secondary eclipse the planet passes behind the star. We watch the combined light of star plus planet, then the star alone, and we take the difference. That subtraction is the foundation of an emission spectrum. What disappears when the planet is gone is by definition the planet's contribution. That's the evidence moment, not a number in operation, a clean conceptual subtraction. And it's why this mode is so powerful. It is built to separate an exoplanet's atmosphere from the overwhelming glare next door. But subtraction is only as truthful as the scale you're weighing with. Between photons and spectrum calibration is the whole story. Calibration means correcting for the detector's quirks and making sure that what the instrument reports corresponds to real brightness at real wavelengths. It's where we decide what counts mean. It's where we map wavelength to pixel. It's where we correct time-dependent behavior. It is also where drift can sneak in and quietly reshape the curve. So we lay out the inference chain in plain language like a courtroom reconstruction, not a revelation. First, photons hit the detector. Second, we correct the detector's behavior to remove patterns that belong to the instrument, not the sky. Third, we produce a calibrated spectrum. Fourth, we perform a retrieval. That last word, retrieval, is one of the most important in modern exoplanet atmosphere science, and one of the easiest to misunderstand. A retrieval doesn't ask what is the atmosphere. It asks what atmospheres could plausibly have produced this spectrum. It's a structured search through possibilities constrained by physics and by model assumptions. Retrievals turn spectra into distributions, ranges of temperatures, compositions, pressure levels, rather than a single tidy answer. And that is where the title's tension bites down. A retrieval can confidently explain the wrong spectrum if the calibration has drifted. So we keep the honesty straight. Emission spectroscopy can probe temperature structure and molecular features because gases and temperature profiles change how radiation escapes. If the calibrated spectrum is stable, retrieval can constrain the dayside temperature profile and the broad composition pattern within the limits of the models used. If the spectrum shifts over time, we might be seeing real atmospheric variability, or we might be watching instrument behavior masquerade as weather. Now we name the specific confounder that haunts this section not as a vague cloud of doubt, but as a test the team must run retrieval priors and model assumptions. This is the quieter failure mode. Even if the calibration were perfect, our interpretation can still be bent by the choices we make in the model. Retrievals depend on assumptions, often a one-dimensional atmosphere, simplified temperature pressure profiles, particular ways of parameterizing composition. Those assumptions are not wrong, they are necessary, but they can be brittle. Here's the tension pair in plain language: model fit versus calibration drift. If the spectrum refused to fit, the temptation is to let the model grow more complex until it fits. But complexity can become camouflage. The retrieval can absorb imperfections, instrument residuals, baseline wiggles, by inventing atmospheric structure that looks scientific because it uses scientific language. So the discipline is to ask what remains true when the model is changed, what remains true when priors are loosened, what remains true across independent reductions. Those are the questions that define what we know as the title promises. And now we tie the thread back to the hook explicitly as we move forward. The story is not WASP-121b is strange. The story is in JWST/MIRI emission. The glow refused to fit, and we have to decide whether the refusal lives in the planet's atmosphere or in calibration drift, and the assumptions layered on top. That decision isn't made with one clever plot twist. It's made with an attitude: treat the instrument like a witness who can be mistaken, and treat your own model like a suspect that can confess too easily. Because here's the hard truth that has to be carried, especially for the search for signs of life. A biosignature claim, any claim, will be built on the same chain: observation, calibration, retrieval, interpretation, and every link can produce a false positive if we stop asking where it might bend. So we end this section by turning the lens. We've traced how the data becomes an atmosphere. Now we pivot to the moment the science gets uncomfortable. What if the atmosphere we retrieved is actually the instrument speaking? What if in the glow that refused to fit the telescope itself becomes a suspect? The room goes quieter when the suspect changes. Not the planet, not the star, the machine. A spectral line can feel like a confession. A slope can feel like a climate. A bump can look exactly like chemistry in an exoplanet atmosphere. But in the wrong light, those same shapes can be something else. A detector settling a baseline, shifting a calibration that slides by a fraction and never announces itself. This is the change of perspective. When the telescope becomes the suspect, the key question is the one we usually try to avoid because it threatens the whole enterprise. What does calibration drift look like in an exoplanet emission spectrum, and how can it mimic atmospheric physics? Start with what we are actually holding in our hands. An emission spectrum is a curved planet brightness relative to its star laid out across wavelength. For WASP-121b, that curve is supposed to be interpretable. It's supposed to be a map, imperfect, yes, but a map of how heat escapes through the atmosphere. In infrared spectroscopy, the shape of the spectrum is exactly what we use to infer temperature, structure, and opacity. And that's why calibration drift is so dangerous. It doesn't have to be dramatic. It doesn't have to look like a failure. It can look like a planet. Picture a dial labeled drift. Turn it gently and the spectrum tilts. Turn it again and the smooth, believable feature appears where a molecule band might sit. Turn it back and the feature softens or disappears. Nothing about that movement feels like a red error banner. It feels like a new atmospheric story trying to be told. This is the tension pair said plainly: planet atmosphere versus instrument systematics. Signal versus artifact. Now we name the confounder with its proper weight: instrument systematics. Thermal settling, detector effects, calibration, drift. Infrared detectors can show time-dependent behavior that changes how raw counts translate into calibrated flux. That's not a flaw unique to one observatory. It's a fact of precision measurement. And in exoplanet science, we are always operating at the edge, where small systematics can become big interpretations. So how do scientists confront that? They don't argue about the planet first. They interrogate the behavior of the measurement. One approach is conceptual. Ask whether the mismatch can be explained by something physically plausible in the atmosphere. Some spectral disagreements are more consistent with a smooth instrumental trend, like a baseline shift, than with an atmosphere that would require extreme, finely tuned structure. Not because atmospheres can't be strange, they can, but because nature has its own kinds of coherence, and our instruments have theirs. Another approach is practical repetition and independence. If you observe again and the same features appear in the same way, confidence rises that you're seeing the planet. If you reduce the data with independent pipelines and the same structure survives, confidence rises again. If the features shift with observing setup or processing choices, suspicion turns back toward systematics. We have to be honest about what repetition can and can't do. If you only have a few looks at the planet, only a few eclipses, then time itself becomes a confounder. And here we name it explicitly, because it belongs in the room-time variability versus sampling. A hot atmosphere could be variable, dynamic, three-dimensional, so differences across observations could be real. But limited sampling can also make an instrumental drift look like variability. A small baseline change across a short window can be mistaken for the planet changing its glow. That's the cruel symmetry. Both weather and drift can produce change. So the discipline becomes a kind of skepticism choreography. You test the signal against the confounders one by one. Does the feature persist when you process the data differently? Does it persist when you rerun the calibration steps? Does it align with expectations across wavelength? Or does it look like a smooth trend an instrument might imprint? Does the retrieval demand a temperature structure that seems delicately engineered to fit a fragile bump? Or does it hold up under stress? This is where the title thread returns with its credibility framing. The glow from WASP-121b refused to fit, and that refusal forces a choice. Either we are glimpsing a truly exotic atmosphere, or we are watching calibration drift reshape the spectrum into something that looks like meaning. The emotional truth is that both options are unsettling. If it's the planet, it means our simplified pictures of exoplanet atmospheres are missing something fundamental, something about heat transport or structure that only reveals itself when we stare hard enough. If it's the instrument, it means our most powerful tools can whisper plausible lies unless we build rituals of verification around them. And those rituals aren't a detour from discovery, they are discovery's spine, because the path to signs of life will run through far weaker signals than WASP-121b can offer. If calibration drift can mimic molecular structure here, it can certainly mimic it on a smaller world where the spectrum is fainter and the stakes are higher. That's how false positives are born, not from fraud, but from hunger. So we arrive at the end of this perspective shift holding two truths at once. Instrument systematics can sculpt an emission spectrum in ways that resemble atmosphere. Some parts of a measured spectrum may be robust to that sculpting, while others are fragile. With more data, the planet might reveal stable patterns that no drift model can erase, or the features might dissolve into the instrument's own signature. Now we step forward into the harshest act of the story triage. The question becomes not which story do we like, but which conclusion survives the most skeptical tests. We carry both possibilities into the next section, and we ask calmly and without mercy, what in WASP-121b's MIRI emission still stands after we account for calibration drift and what has to be set aside for now as uncertainty. The spectrum is still there, quiet, unimpressed by our arguments. A curve doesn't care what we hope it means. It only asks one thing of us: do we have the right to interpret it? This section is limitation heavy by design, because if we're honest, the most important product of an exoplanet atmosphere measurement is not a headline. It's a map of what survives stress and what collapses when you touch it. The key question now is blunt. After accounting for calibration, drift, and modeling limits, what can we honestly say about WASP-121b's emission and atmosphere? We start with the posture the title demands. The glow from WASP-121b in MIRI emission refused to fit, and the refusal forces a kind of scientific triage, separate the robust from the fragile, and refuse to let a delicate feature become a strong claim. So picture the spectrum as a field divided into zones. Some regions are marked robust. They barely move when you change reasonable calibration choices or run independent reductions. Some are marked fragile. They shift, they soften, they might even invert. And some are unknown, not because we lack imagination, but because the confounders can plausibly dominate. This is the evidence moment in this section, not a new measurement, but a diagnostic posture. A before and after comparison, what the spectrum suggests before drift concerns, and what remains after drift is treated as a real suspect. Here is what holds at the broadest level. WASP-121b is an ultra-hot exoplanet where thermal emission can be strong enough to measure detailed spectral shapes. That alone is a constraint. There is detectable day-side heat leaving the planet through an atmosphere that shapes the outgoing radiation. This is not a philosophical statement. It's the foundation of why emission spectroscopy is even attempted. Now we move one step inward carefully. Broad properties often remain steadier than narrow, intricate claims. The overall brightness pattern across wavelength can still constrain a range of possible day-side temperature structures and overall opacity behavior, even if individual bumps are suspect. The exact details depend on the stability of the calibration, but the principle is firm. The hotter and brighter the day side appears, the more the atmosphere must permit certain wavelengths to escape from certain depths. That's the part of interpretation that can sometimes survive drift tests because it relies on larger scale behavior rather than a single small feature. Now, the hard part, any specific molecule identification must be treated cautiously if it depends on subtle features vulnerable to calibration drift. This is where many viewers expect the story to become more definitive and where the discipline demands the opposite. In retrieval, it is tempting to assign every bump to a gas, every slope to chemistry. But if a feature can be produced by instrument systematics, if calibration drift can create it or reshape it, then calling it a molecule is not knowledge. It's an unearned inference. So we name the confounder again explicitly because it owns the section instrument systematics, calibration, drift wavelength calibration, uncertainty detector effects. If those systematics are comparable in scale to the features we want to interpret, then the error budget is not a footnote. It's the main plot. And the honest move is to downgrade certain claims from likely to not yet even if they fit beautifully. This is where the second limitation enters not as a replacement suspect, but as a parallel ambiguity that can complicate interpretation even when calibration is stable clouds and hazes degeneracy. The name sounds gentle. The effect is brutal. Opacity sources in an atmosphere can mute or smear spectral features. Even on very hot worlds, additional opacity, whether from aerosols or other sources, can flatten features and leave multiple atmospheric explanations consistent with the same spectrum. That degeneracy means that even a stable spectrum may not uniquely determine composition. It can leave you with a family of plausible atmospheres rather than one. Now we fold in the model side without re-explaining tools, just the limitation. Retrieval is not an oracle. It is an argument constrained by assumptions. If a retrieval is built on a simplified one-dimensional picture of an atmosphere that is in reality three-dimensional and dynamic, then some of the best fit structure may be a projection true and the math misleading in the world. This is why limitation heavy isn't pessimism, it's fidelity. So what is the best current conclusion under all that restraint? It sounds almost modest, but it is the kind of modesty that keeps the field alive. WASP-121b measured emission indicates a hot day-side atmosphere whose broad thermal behavior can be constrained, while finer-grained claims, especially those hinging on subtle spectral features, remain sensitive to calibration drift and modeling degeneracies. That is the conclusion that survives, not because it's satisfying, because it's durable. And now we allow one forward-facing speculation exactly at the boundary the outline permits. With improved calibration and repeated observations, repeat eclipses or phase coverage, some currently fragile features could harden into robust constraints, or they could disappear revealed as artifacts. The point is not which outcome we prefer. The point is that only future data can decide, and we can name what kind of future data would matter without pretending it already exists. Now we connect this directly back to the title again with credibility framing. The glow refused to fit, and that refusal wasn't a failure. It was a stress test. It forced the case into the open MIRI emission versus calibration drift, and the only honest output is a hierarchy of confidence, what we know, what we infer, and what we can only speculate. This is where the episode turns outward without leaving the micro niche. Because if this is how difficult it is to interpret a loud atmospheric signal from a blazing hot giant, we have to ask what it implies for the quieter, fainter targets, the ones where the question might someday be signs of life. The transition isn't hype, it's gravity. We step from a bright, unforgiving planet into a dimmer dream. If calibration drift can masquerade as atmosphere here, what happens when a small spectral bump on a smaller world is tempted into a biosignature claim? We go there next carefully, because the discipline we practice on WASP-121b is the discipline that will protect the search for life. The spectrum fades, but it doesn't leave. It lingers like afterimage, one curve dissolving into another. The loud glow of WASP-121b gives way to a quieter simulated trace, a smaller world, a weaker signal, the same thin slivers of light, same idea, higher stakes. And suddenly, the story isn't only about one ultra-hot exoplanet atmosphere. It's about the kind of restraint that keeps us from mistaking our own instruments for aliens. This final section is reflection with a named unknown that is measurable, not mystical. The key question is the one that sits underneath every future announcement. What does refuse to fit teach us about the day when a small spectral bump could be framed as signs of life? We don't pretend WASP-121b is about habitability. It's not in the habitable zone. It's not a biosignature target, but it is a rehearsal for the moment when an exoplanet spectrum is faint enough that uncertainty stops being a nuisance and becomes the deciding factor. Here's what we can say plainly. Biosignature and technosignature claims require extraordinary control of systematics and astrophysical confounders. The evidence will live in spectra patterns across wavelength just like this. The difference is that the signals will be smaller and the false positives more persuasive. And now we tie back to the title's promise with the credibility framing it demands. The glow from WASP-121b refused to fit, and that refusal is a gift if we treat it correctly. It reminds us that interpretation is earned, that what we know begins only after we've tried seriously to prove ourselves wrong. This is where technosignatures can be mentioned, but only as the outline allows and only with caution. In this channel, technosignatures mean hypothetical signals in exoplanet observational channels, unusual atmospheric industrial gases, strange reflectance, anomalous night-side light things that would still arrive as photons and become spectra. And for now, all of that sits firmly in the realm of the point isn't to chase it. The point is to understand what would fool us if we did. So we anchor the reflection in method, not fantasy. Techniques refined on emission spectra now can harden standards for interpreting weaker signals later, including transmission spectra. The same habits apply: repeat observations, independent reductions, stress tests against instrument systematics, and retrieval checks against model assumptions. If we can't practice discipline on a bright target like WASP-121b, we have no business claiming certainty on a dimmer one. But we also have to admit the confounders will multiply as targets get smaller. This is where we name the specific limitation the outline calls for. In this closing section, stellar contamination, stellar heterogeneity spots and faculae. Stars are not uniform light bulbs. Their surfaces can be modeled and changing. and that imprint can mimic or distort atmospheric features. On small planets, this becomes a central threat: planet atmosphere versus star contamination. Biosignature hope versus false positives. If you want a single sentence to carry forward, it's this: the universe is complicated, and so are the tools we use to read it. Our job is to separate those complications without pretending we can erase them. So we land the reflection in something calm and practical. The discipline we used here, treating calibration, drift as a live suspect, downgrading fragile features, refusing to overinterpret, doesn't slow the search for life. It protects it. Now we end with the named unknown measurable, exactly as the outline specifies. The unknown is not, is there life? It is MIRI calibration, drift amplitude, and wavelength dependence across repeated WASP-121b eclipses. A baseline stability question, a curve behavior question, something you can measure, model, and test. Because if the drift size and its wavelength pattern can be pinned down across repeat observations, if independent reductions converge, if features persist under stable baselines, then what refused to fit can become something we trust. And if those features dissolve, when calibration is improved, that also becomes knowledge about the instrument and about the limits we must carry into every biosignature conversation. The final image holds on that original visual anchor, the emission curve suspended over darkness, the fit line held just apart, not as failure, but as honesty. A reminder that awe is not the opposite of skepticism. Awe is what remains after skepticism has done its work. Sometimes the spectrum is a confession, sometimes it's a mirror. And the difference, especially when we are searching for signs of life in an exoplanet atmosphere, is the discipline we bring to the light.